So, density. First off, as you can see, this illustrates things with a high amount of density have lots of particles packed in a very small space. This is all about particle packing. Low density stuff has lots of more space. As we heat something up, the particles move faster and thus they tend to spread out, which is why hotter things tend to have a lower density than colder things. Liquids have a lower density than solids, and gases have an incredibly low density compared to the other two. So understand that this is comparing mass, which is stuff, to volume, which is space. So this is comparing stuff to space. A high density's got a lot of stuff in a little space, or a low density has a little stuff in a lot of space. Now, we can use this to tell what something is, which is the essence of the lab activity that you are going to be doing. We can figure out what something is based on its density. Here's some samples. To the left, you can see that we've got our, let me turn my pointer on. We've got our water. We've got liquid water, solid ice, and water vapor. And as you can see, the densities are 1 to 0.93 to really, really low, 0.0013. Now, when it comes to this, water is weird. Water is one of the only substances where the solid is less dense than its liquid. Like everything else, if you were to put its solid in its liquid, it would sink, but not water. Water don't do that. And as you can see, metals have a higher density, non-metals. That's not always true. That is not a hard and fast rule, but it is something that in nature, metals do tend to be some of the more dense things that you will encounter, metals and stone. Now, the units are grams per milliliter, which is the same as grams per centimeter cubed, because a milliliter is a centimeter cubed. So those two things are done interchangeably. The units can also be expressed as kilogram per liter, because that's the same thing. I don't really have that expressed often, but that's how your density animation expresses it. It's more done overseas, I guess. The formula, sorry, West Coast, I meant West Coast. It's more done on the West Coast than here. Here we're gram per milliliter, there that's kilogram per liter, but it's the same thing. The formula for density is D equals M over V. And I like to remember this as the DMV of chemistry, you know, because D equals M over V, DMV. Just like the Department of Motor Vehicles, which several of you teenagers may have to encounter soon enough. To be honest, this formula is less useful than you might imagine, and there is an even least useful thing than the formula. The formula is not bad. The formula works. We're going to talk about the formula for the majority of today, but there is a better thing we can do with density using it to convert, and that is going to be what we cover next week. Next week, we're going to cover conversions, and you're going to find that density is better used as a conversion more than just as a formula. But in any case, we're going to look at the formula for now. This depends on the substance, doesn't care about how much of it we have. A tiny little cube of lead has the same density as a pickup truck full of lead. It's all 11.34. If the density is greater than 1, it will sink in water. If it is less than 1, it will float in water, because water is a density of 1. So this determines whether something sinks or floats, which is pretty cool. And understand that density is a derived unit. That means a unit that is based on other units. We are going to encounter like 5 derived units in this class, and density is our first one. There is an awesome video on putting an anvil in mercury, which is right here, and I'm not going to have it autoplay. You can go watch it yourself. It's very much worth watching. When I look at the formula of density is D equals M over V, and like I said, we're going to focus on the formula this week, and then we're pretty much not going to use it later because there's a better thing to use than this formula. You may go, Mr. D, why are you showing us the formula then? Because it is useful and it does work, it's just there's a better thing that we'll learn to do with it next week. Density is your grams over milliliters, which equals your mass, in grams over your volume in milliliters. So notice G per ml equals G per ml. You can, kind of double check it. What you're going to learn, especially next week, is the units are like the best way to guide you. If you make sure the units match, chances are you'll be fine. Now, manipulating equations. When we do this, if I want to find what m equals, okay, what I need, you know something, I didn't want to do it like that. You know, I really hate that this thing doesn't have a writing tool anymore. That is so annoying. All right, let me go switch this up. Always have two things ready. If the writing tool isn't working, you find another tool and you use that. So here we go. Let's get this tool done. I apologize for the delay as I put up my secondary writing tool, but I keep forgetting that Google does for some reason canceled its writing tool. Like, I don't understand that like, at all. But I am not Google. If I was, I would know everything about you, and I'd be very rich. All right. Not quite as rich as Amazon, but still pretty good. All right. Why are you not letting me select things? There we go. Okay. Doop-a-doop-doo. Let's do this. So I'm going to load the other tool. Okay, so now you're going to have a little bit of inception for a minute as this reloads. Okay, so here we go. Well, now I loaded my secondary drawing tool. So it basically goes like this. We know that D equals M over V. That is our identity. That is what we've been told. So the question is, well, what if we wanted to find what M equals? Okay, what if that is our goal? So what we can do is we can manipulate the formula to get M alone. To do that, we're going to times both sides by V. Because what you do to one side, you have to do to the other. And since V is on the bottom, I want to get rid of it so that M is alone. So they cancel, and now I've got M equals D times V. So M equals D times V. So there's my first manipulation. But what if I want to get volume alone? So if I want to get volume alone, it's a little more complicated. To start with, I still start with my D equals M over V. If I want volume alone, it's already on the bottom, and that's bad. I never want what I want on the bottom. I want what I want on the top. So I'm going to multiply both sides by V. Look familiar? And that'll cancel it here, and I will be left with V times D equals M. But I don't want M. I want V. So I'm going to divide both sides by D. And that will give me my final answer of V equals M over D, like that. So that's me manipulating the equation. And I mean, at this point in your high school career, you should be able to manipulate a simple 3-variable equation. But if you can't, then hopefully that helped. Hopefully that understood. And you're going to want to seek help. You're going to want to ask me. You're going to want to sit down with me during office hours or during one of our work days, which should be coming up. I believe we're going to be having a work day next class. But there's your manipulating formulas. Oh, I didn't want to do that. I want to do this. And then you can sit there and you can see it all comes in if you just click it, but it's not as useful. This is even better because this showed how I did it back in the day, and I really liked it, so I saved it. But density is your base, getting mass is your first flip, and the volume is your second. Now, calculating the density. This is plug and play algebra. It's not that, it shouldn't be that challenging. It should be very easy for you to do. You copy the formula, you fill in the info. You then solve, and you want to round. Now, for now, round to 2 decimal places. You will learn how to round properly tomorrow, but don't worry about it now. What you really round by is how many digits you started with. So I started with 3 digits here and 3 digits there, which means my answer should be in 3 digits, which it is. But you can just do 2 decimal places until tomorrow. So you can just do that for now. Tomorrow we'll be talking about why. But basically, if you look at how many digits you start with everything the problem gives you, 3 digits, your answer should be in 3 digits. More on that tomorrow. So, and then, you can sit there. This is my little step on how to do that. So there you go. And again, you want to round, and it's not based on 2 decimals. It's based on how many digits, but 2 decimals will work for now. And so you can sit there and see if I'm doing mass, if I'm doing volume, what's that going to look like? Well, again, I use the different formula. I use the m equals dv, which is my altered formula. As I put that there, you'll notice the milliliters cancel, grams are left behind, and I have my unit. Again, 2 digits because I had 3 and I had 2, and we used the lowest. Over here, I'm going to change that from decimals to digits because you should just go right to that. Over here, if I do this, the grams cancel, the milliliters get thrown to the top because when you divide a unit that's already being divided, it gets thrown to the top. You can feel free to talk to your math teacher about that more. I'm not going to go into it. That's just how it is. Because an anvil, a huge 500-pound anvil can float in mercury because of density. As a physical property, density is affected by the phase it is in, solid, liquid, and gas. As it gets hotter, the density tends to get less. Again, except for water. Water is weird. We'll talk about that later. Particle diagrams basically are drawings where you draw little particles and you talk about how big they are, how far they are, and whatnot. It's a very useful way to interpret mass, to interpret matter, and how they interact with each other. We will be doing particle diagrams randomly throughout the course because they're very useful to show how the atoms and molecules are working at that time. And as you can see here, there are some questions where it talks about comparing the mass, the volume, and the density of these 3 blocks marked A, B, and C. So comparing these 3 densities, or comparing these 3 blocks, both in mass, volume, and density. Mass, A has more dots, period. Then B, C, then B. Done. Simple, easy. You count the dots, the more dots, since each dot is a gram. A's just got more stuff. Now for volume, A definitely has more, but B and C are copy and pasted. They are exactly the same space. So B and C has the same volume. But when we get to density, you'll notice that C has the highest density, and that is because its pieces are really close to each other, whereas the other ones are more spread out. A and B have the same density because they have the same amount of pieces and space between pieces. So again, copy and pasting to make sure they were identical. C, however, is tightly packed. So this gives you an idea. C would sink if put in A and B. And if you mixed A and B together, they would just mix throughout each other and they really wouldn't sink or float. They'd be exactly where you put them, which is pretty gnarly. Of course, A and B may end up being the same substance. You can then take a look at this graph that is here. Now, first off, your graphs don't have to start at the origin. I just had this one start at the origin because it makes the idea similar. When you make a graph, it'll almost never start in the origin because that is statistically improbable. In like real life, error is a thing. So will it float in a bucket of water, and calculate the density? Whew. So how do we do this? Well, quite frankly, we need to know what water is. So what we do is we need to draw water's line in there. Now, water is 1 for 1, so you literally are making it that, okay, here's the 10 for our volume, so it needs to be 10 mass. Here's our 20 for volume, so 20 mass, and then just a straight line. So if you look at this line here for water, you can see that it's got its density. Its density winds up being its slope right there, okay? Because that is your mass divided by your volume. So, 10 by 10, 20 by 20, 30 by 30, 40 by 40 gives you a density of 1. You can use that same idea to try to figure out these other ones. Okay, if you see the dark blue line will float in water because its slope is less than 1. Its angle is not as steep. As such, it will float. It is less dense than water, whereas the red one is more dense than water. In fact, it's twice as dense as water. If you go up to 10 on your volume, you've got 20 grams, which means its density is 2. So, and you can, see that you've got 0.67 because I believe that one was supposed to represent gasoline or an oil. And then you've got, 2 being the red one. And again, you calculate that by mass divided by volume, gives you slope. Slope is density. There you go. Now, remembering your densities that you got earlier, if I use this two-pan balance, which is something that like you don't see much anymore, but it used to be like a real big deal. What if we place the same mass and volume? Well, first off, if I put the same mass in these two-pan balances, yeah, it should just be stable. It's not going to go either way because it's all based on mass. Volume doesn't matter in a balance. Balance is all about mass. If I put the same volume in it, though, it would then tip to the right because B has a much greater density. So the same amount of volume would make it so that the mass of B would be significantly higher than the mass of A. Again, because it's all based on mass. You've got the introduction to play with and learn about density. When you can click the second one, compare, to see direct matches of mass and or volume, giving you a bit of a better thing. And then try to figure out the mystery blocks. Now, I went and this is actually the old version that's up here. The new version looks different than this. The new version actually looks a little kind of like it just looks a little different. But basically the idea is the same. You mass it, then you drop it in, and you take the difference. And for your mystery blocks, again, they just updated this because it used to be based off of Flash, and Flash is dead. Nobody should use it. It is a very compromised program, super full of viruses and problems. So like all modern browsers just don't let it work. So they're updated to HTML5, which is a lot more secure. And there's your nerdy lesson for the day that you get from your chemistry teacher. Now, then you have these density lab slides. These slides go over how that density lab data was collected. So it talks about finding the solid. It talks about, so I'm going to close this for now. And we're just going to go here because it's slowing things down. It's just going to keep slowing things down. That's fine. So you find mass with the balance, volume with the cylinder. The odd shapes don't matter because we're using water displacement, where the water will fill in the gaps, and we find the difference between the starting and the ending volumes. This would be the volume of the solid. So if you have like a rubber stopper and we roll it down the side and it had 10 mLs, and once it's in there, it has 30 mLs. So what is the volume of the solid? Who the volume of that solid is? Feel free to unmute, say your name, and then give me the answer. Nobody?
Is it 20? Oh, Johnson, 20.
Sorry, can you say your name again?
Johnson.
Okay, Johnson. What's your last name, Mr. Johnson?
Jay.
Jay, okay. Got it. Okay, is it 20? If you refer to 20 milliliters, yes.
Yeah.
20 mLs, and that is because you take the final minus the initial, and bam, you get your answer. Okay, wonderful. Enjoy your extra credit point. Thank you for participating. That extra credit point will emerge in probably about 2 weeks. Whenever I do extra credit, I calculate it at the end of every short-term grading cycle. So it's basically about 2 weeks. If you take a look at this for this data table that's there, here's my sample data table. Okay, here was the mass. This was how much water was in it at first. Then I had my water plus my solid. Notice I used a different tool for the large stopper and the mini stoppers. My tool did not have a decimal place. It wasn't a very good tool, but it was very good for the size that I was dealing with. So you'll take the water plus solid, and you'll subtract them. You'll take the 84 minus the 61, gives you 23. And that gives you your volume. Your mass of whatever you care about, in this case the solid, divided by the volume of the solid gives you density. The densities here, then all get added together, divided by 3, 1, 2, 3, so that I can get my average. Now, when you have something that is a single small stopper, any error is magnified. So that's why this number, the 1.5, is actually different from the 1.2s, and it's a little less trustworthy. Because smaller things are more prone to error. But weighing many things reduces the amount of error you have greatly. So this is the most reliable number, which happened to match what I got at the first time. So it was kind of nice. Now, so I don't know why that showed up. I won't care about that. Okay, this is me doing basically that. Okay, you should watch this video because I make a mistake, there are errors, and I talk about significance, which is tomorrow's topics. This is a pretty good video for you to watch. I was very happy about its recording. So yeah, you can watch that later. Now, getting the liquids are easier. You put the cylinder on the balance, you zero the balance, you add the liquid sample, you find mass on the balance, volume on the cylinder. So it's really cool. You just put the cylinder on the balance, you zero it, so the balance ignores the weight of the cylinder. Then as you add liquid, you will get both of the volume and the mass. And if you did this, if like you had a computer doing this for you, it could like immediately graph the data and put it all there, which is pretty cool. I got to do that once. And then you just keep adding more liquid and you record new values for each another trial, which is pretty, awesome. So let's say in this large cylinder, I wanted about 30, about 60, and about 90. These abouts just told me my target. Notice my about 60, I put 71.8 in, but that's okay because density does not matter on the size of the sample. And you can see I had a student helping me out who signed his name here with my permission so that he will be immortalized forever